this computer. Okay, I hope you all tried the assignment like I said. And so Nermin, just enjoy. Enjoy this lecture. Like enjoy learning how to, a little bit more about.
Definitely, I will. No worries.
Okay, so enjoy the lecture. How's that? Let's just. Okay, sounds good. Okay.
Yeah.
So. Okay, so here was the. Okay, I like to annotate all the time. So. Okay, so this was the problem. Okay, we had a W610 by 82. I hope you guys are starting to appreciate that a 24-inch beam starts to be a substantial size beam and 82 kilograms per meter. Well, that's also starting to be a nice weight for the beam. And like I said, this is the American steel, and most of all the Ws are being milled and rolled in the United States, and that's why we don't use the CSA anymore. We tend to specify the American steel, and like I said, the grade 50 means that instead of getting 350 MPa, we're down to 345. In other words, we have the strength is 50 KSI. So we lose about 5 MPa on the strength, and it has a span of 9 meters. The beam is laterally supported at midspan. So now here, what happens is that there's only one thing that's going to prevent the beam from moving laterally in plan view. So therefore, we know what. Now calculate the uniform distributed load WF, which the beam can support. Check the shear, okay, of the beam. And I think there was something else here, but I'll repeat it afterwards. So basically, since we only have one place where the beam is laterally supported in the middle, so therefore the unbraced length of the beam ends up being 4,500 millimeters. And as I said, guys, this is the most important thing to keep in mind when you go to the tables, okay? Because this is going to basically decide whether or not you're doing the right thing with the table. So this is the first thing you should consider and establish whenever you're designing a beam, okay? So what is the unbraced length of your beam? Now, so now we'll go to the, so it's a W610 by 82. I'll just keep that in mind. So W610 by 82. Okay, here we go. So here we go. We have a W610 by 82 here, okay? And unfortunately, I cannot see where the fourth, okay, the 4,500 is the second column. So the first thing I do is I look at, okay, I look at what the unbraced length is. So this is the unbraced length at 4,500. Now, I didn't talk about this last week. I'll talk about this now. The reason why there's hyphens here, okay? The reason why there's hyphens here, if you look at the unbraced length here, okay, this length is still greater than this one, still greater than this one, still greater than this one, still greater than this one. Therefore, up to 4,400 millimeters, the MR value is still 1,470. So that's why you see these blanks. So whenever you see these blanks, that means that the LU value here is greater than the values in this table, and therefore you can still use the MR value. So that's why, okay, so if all of a sudden you come down at 4,000, you see a blank, well, go here. That means you can go ahead and use this MR value. I forgot to explain that last week, and I apologize. So what that's what that is, and therefore we're going down to the second column, and of course we want to make sure that we have a W. So we have a W610 by 82. Okay, and therefore here you can appreciate what happens here. The LU of this beam, the maximum unbraced length is 2,110 millimeters, and then that would give you a resistance 683. And because it's only braced at 4,500, it almost loses half its resistance. Okay, so therefore the MR value for that unbraced length will end up being 364 kilonewton meters. And while you're here, you might as well get the value of MR. I'm sorry, you might as well get the value of VR. I'm sorry. You might as well get the value of VR, and you might as well get the value of IX, because you're going to be needing that to do other calculations. And that's where you get that. So when you're at the table. So here we go. So now we have our MR value. So, oops, I should have cleared the drawing. So we have an MR value of, like I said, now here I put MR prime because it's really, it's got a longer unbraced length than the maximum unbraced length. So I use the MR prime. And of course, that still has to be greater than MF. And therefore, I'm assuming that this beam is, you know, has a uniformly distributed load. Therefore, the MF value is equal to WFL squared over 8. And of course, what's the maximum WF? You just isolate the WF and you end up getting, and don't forget the span, and we end up getting 35.95. Okay, I would have used 36, but I put it in two decimal places, 35.95 kilonewtons per meter. So in theory, this is the maximum factor load that this beam can carry for that unbraced length, and therefore I would not, if I want to keep it to have the same margin of safety required by the limit state design, I would not go exceed that value. Okay. Now, so of course, VF is equal to WFL over 2 because it's simply supported, and therefore we end up getting a VF of 161.8 kilonewtons. Now, the VR value, we got that from the table, 1,170 kilonewtons. And of course, I always said that in order to anticipate that if you need to make holes for your connections, you should take 80% of the VR value. So this is just good practice, okay? So you take 80% of the VR value here, and even at 80%, you still have sufficient, very much resistance in shear, and therefore you have absolutely no problem. So even at 80%, there's no problem, okay? So that's your VR value. Now, after that, I think I said, assume that the live load is 2 times greater than the dead load, because I need to give you some kind of ratio. But in real life, if you're actually checking an existing beam, you would have actually calculated the dead load, because you'd be able to go and see everything that the beam is carrying. And then after that, you can know what the ratio is of dead load versus the live load. Calculate the deflection of the beam due to the dead load and the deflection of the beam due to live load, okay? So basically, what we're saying is that WF, and of course, we take combination or case number 2 combination. So I take 1.25 times my dead load and 1.5 times my live load. And of course, I say the live load is twice the dead load. Therefore, I just replace L by 2D. I end up getting 4D, and therefore I end up getting the dead load. Now, this is the specified dead load, okay, of 8.5 kilonewtons per meter. So that's my specified dead load. And of course, if I want to know what my live load, I just take 2 times that value. That's 17, okay? So this is the specified load that you would actually, so if this beam had a tributary width of, I don't know, 4 meters, and therefore the maximum live load would be divided by 4, the maximum specified load you'd have is, what is it, 4.24 kPa. That's what you do. Okay, so now we have that. And now to calculate deflection, of course, this is the equation I had to use for calculating deflection, 5WL to the 4th over 184 EI. Now I put D here because I want to calculate the deflection due to dead load only. And of course I use IX. Why? Because the beam, okay, because the beam is actually going to be, okay, the beam is going to actually be bending with respect to the XX axis, okay? And you'll start seeing that we are also going to start worrying about the YY axis when it comes to columns, but this is why we use the IX value, which is much stronger than the moment of inertia with the Y axis. Okay, I'm just going to repeat that so you guys, and therefore, now the only thing I need to do here is remember that I need to put my span in millimeters in order for all the units to work out. Otherwise, the units will not work out. Okay, and if you don't do this, you'll get an astronomically small value for delta D. And if you look, the units do work out. This cancels that cancels that cancels that. You end up with millimeters. So you've got the right units. So you might as well, now you can do the calculations. And I have a deflection of about 1/4 of an inch. Now, if you really want to get, if the client wants to make sure that his floor is absolutely straight once the dead loads are implied, that means that you would camber the beam and you would ask for a camber, okay? You would ask for a camber. In other words, what they would do is they would camber the beam and they would make sure that this camber here is 6.5. I would even specify a 7 millimeter camber just to be on the safe side. okay? And there you go. So that's what they would do in this way when the loads all come down, and it will come down, it will be nice and straight. So that's for your dead load. That's why we calculated the camber for dead load. And now for the live load, same equation. The only difference, I use the live load here, and I end up getting 13 millimeters. And of course, if this beam is carrying something susceptible to cracking, we know that the maximum deflection is L over 360. So the maximum deflection is L over 360. Therefore, I take 9,000 divided by 360. I'm allowed to go up to 25 millimeters. I have only 13. So this beam would be stiff enough to make sure that anything that's going to be supported by this beam is not going to, or it won't be susceptible to cracking. And I think, oh yeah, then we had another question, and here, determine the lightest. Oh yeah, before I move, everybody okay with this? Just sounds good.
Yes.
Yes, sir.
Okay,
Yeah,
now,
thank you.
Thank you.
okay,
Yes, sir.
okay, now determine the lightest white flange beam that is simply supported with a 9-meter span, okay, which carries a dead load of 1 kPa, including the self-weighted beam, okay, and a live load of 2.4 kPa, which is reasonable, which is 50 pounds per square foot. The tributary width of the beam is 7.4 meters. The live load deflection is L over 360, and the beam is lightly supported at mid-span and at the supports. Okay, so now we know. So now case
Sir,
one, yes.
I'm sorry for cutting you off. For question one, could you go back to your table where you chose your MR, please?
For the, in other words, where I picked the MR value. Is that what you want
Yeah,
to know?
exactly.
Okay, so you're talking about, you go to the beam selection table.
Yeah, please.
Okay, remember, before you go to the table, Arvel, you got to worry about this value here. You see this?
Yeah, I did that, but for some reason my MR I took 123 instead of 364. I don't know why.
Well, this is, Marvel, let me tell you one thing, okay? Let me tell you one thing. I come to the table. This is what I literally do, okay? In other words, I have a hard copy. If I'm doing this on the screen, I literally do this, okay? I draw a line here, like this, okay, on the screen, and then I go look here like this, and then I make sure that I'm picking the right value.
I don't understand why I took 123. There's not even 123 close to there.
No, exactly. So you must have been looking somewhere else. In other words, the first thing I worry about is make sure that this is absolutely right. So therefore, I go there, and then, like I said, I draw a line right across here, okay? And then after that, once I know I'm at the right designation, okay, I go and I look at the LU value, and then I pull a line all the way down. And I do this constantly, Mario, because like you said, it's pretty silly. You go through all these calculations, you go to the table, and you accidentally take the wrong value. So everything you've done is in vain, right?
Yeah, exactly.
Okay, so keep that in mind. So do that, and as a matter of fact, whenever I'm designing anything, guys, okay, I do this. I try to be as careful as possible the first time around. Then I take all my calculations, I put them on the side. The day after, when I wake up, when I know I'm really fresh, and I redo my calculations. Okay, and if I don't get the same answer, then I'm glad I redid my calculations. And if I did the same answer, well, I sleep better at night. Okay, so guys, don't just do this, because any mistakes you make, if you don't, and if you don't realize a mistake you made, okay, unfortunately, sometimes it can have some dire consequences, and that's the last thing you want to have to face. You understand? It's nothing but a lot of waste of time when you do something wrong, and somebody's going to come after you because you did something wrong. So keep that in mind, okay?
Thank you,
And,
sir.
okay, you're welcome. No problem. So, like I said, if you would have had a hard copy of this, and if you would have highlighted, Harvell, where you took your value, you would be able to go back and see where you made your mistake. But if you didn't do that, you'll never find out why. You understand?
All right, perfect.
So God knows where you were here, or God knows where you were here. Like, there's two variables here, so we can't go and see what you might have done wrong. You understand?
No problem.
No problem. Okay.
Yes, sir.
Yes.
Wouldn't it be better to take the LU of 5,000 instead of 4,500?
Oh, we have
Since
an
it's
LU of
almost
4,500 in our
yeah, but
problem. So
Yeah, I know, but since that's the maximum, would we be better, like, safer if we used 5,000?
if you want, but you do know that you have 4,500. So like, look, there's nothing to stop you from being safer. So if you want to take 5,000, go ahead. That
Yeah, I was
means
just
you
asking because since 4,500 is like the maximum we could use for.
no, 4,500 is your unbraced length. In other words, what they're
Yeah,
saying
that's
is
the
that,
maximum on burst length, no?
no, this is the unbraced length of the beam. Okay, so for this unbraced length, it's going to have an MR value of 364. Now, for example, if this beam, okay, if this beam was supporting a steel deck, okay, a steel deck, and the steel deck was spot welded at every 300, which is usually how they do it. In other words, these spot welds would be laterally supporting the beam at every 300. Well, all of a sudden I'd be able to take the same beam and get this value out of it because it's laterally supported every 300, because then the LU provided is only 300 and the maximum is 2,100. So the LU, these values here, okay, have been adjusted based on the fact that the beam, like if you go back to the first lecture, you understand what happens is that what they want to make sure of is that since this is in compression, it doesn't buckle on you. You understand? You don't have a local failure. And that's why they say, what is the maximum length I can have here so that this thing won't buckle on you and the beam will be able to develop its full strength. So here what they're saying is that if this beam has a length of 2,100, okay, then it can go up to its actual MR value. But as this length becomes longer and longer and longer, okay, then it's more subjective. And when we do columns next week, you'll appreciate what we mean by you understand, the fact that it can buckle, and that's why they have. And then on top of that, today in the lab, I'll show you, this morning in the lab, I'll show you what's required when you have an unbraced length. You'll see how involved it is in doing the calculations. And as a matter of fact, what you can do, and I'll repeat this in the lab, you can take what I'm going to give you in the lab, because I already sent you the Excel spreadsheet, okay? And if you take that spreadsheet and you put a value, I'll show you where you put a value of 1, and you can come to this table, you'll get exactly the same value that you get in this table. You understand? So that's all this is that. So if you want to use this value here instead of that value there, by all means, it's up to you. But what they're saying is that at this value here, you can, get that kind of a resistance. So it's up to you guys. But I will not, nobody's going to penalize you for being more conservative. Trust me, only your client.
So I have another question.
Yeah, go ahead.
When did you say that we have to use the other side of the table? Because I think that's what I did. I used the 123 under the 9,000 millimeters.
Well, that's because you took an unbraced length of 9,000. In other words, this thing was not laterally supported at all. It was only attached at its supports.
Oh, okay,
You
perfect.
follow what I'm saying?
Right.
So in other words, if all of a sudden, like, let's say this is my beam here, like this, okay, and it's being supported here, and it's being supported here, and all of a sudden I have a load hanging here from it, right? Just hanging here. There's nothing. In that case here, this whole thing is in compression. Therefore, your LU would be 9,000,
Okay.
and therefore that would be the right value to use. You
Okay.
follow?
Yeah.
So in that case, you're absolutely right. You understand? And as a matter of fact, that's what you should be using, because you're just hanging this down here. There's nothing up here to prevent this thing from moving laterally, and therefore the embrace length becomes 9,000. So you're absolutely right for that case. You understand?
All right.
Okay. In this case here, what we're saying is there's probably another beam that comes in here at the midspan, and this beam is going to give it some lateral support, and therefore we only took half of it. That's all we're saying, okay? Okay, so let's go back to where we were. Now, okay, that's it. Now, oh yeah, we did this. Okay, so here we were. Okay, we're at case number 2. Now, remember that, of course, case number 2 is one that governed. Now, of course, remember, how do you change this from a pressure, in other words, from a force over a surface area, to a uniformly distributed load? Well, you take the factor load multiplied by the tributary width, and here it's given to you. And therefore, we have, okay, and then of course you need to know this for your deflection. And therefore, we also have WL for deflection to calculate our moment of inertia required. So we have our MF value of 363, 363.5. I'm writing this down because when I go to the table, I want to remember, okay, the VF I won't worry about right now. And the IX I'm going to want to worry about. Well, I'll worry about that after. But what I'm really worried about is, of course, before I go to the table, I should know what my LU value is. And I believe my LU value here was 4,500. Okay, and we have an 4,500. So I look at 4,500 where I can find a value of 363. Okay, so 4,005. Oh, sorry. $4,500. So there's nothing here. For 363. So this is no good. Wait. Oh yeah, 364. W610 by 82. Okay. W640 by 74. So let me go back. Sorry, I didn't know. Okay, so my LU value. Okay, sorry. Okay, so what is it? W640 by 74. W640 by 74. Where's W640? Here you go. There you go. 375, which is greater than my, you understand? So I could use a W640 by 74, okay, as opposed to going further up where I would use a W610 by 82. So therefore, the lightest section I can find is that one right there, okay? So like I said, I would go into the unbraced length here until I find an MR value greater than my MF value, and then I would go check to see if this weight here is the smallest value, because I really don't care. And then of course I would have to worry about moment of inertia, and I'd have to worry about shear, but I start by this, and then I go and check these two values. So I have an LU of 4,500. I should have put this above because I forgot what my LU provided was. Now the MF, okay, the VR value, and the IX is okay. So therefore, that would be the lightest. So if I give you a problem where I want you to find the lightest section, I expect you to go look for the lightest section. And of course, if you give me something that works, but it's not the lightest section, it's going to cost you a few points. So keep that in mind. And I think that's it. Okay.
So I have a quick question about the beam table.
Yeah, okay.
Because I was struggling to find like a beam. So when we have our MR value and everything, we should use that to determine like to choose a beam, and we gotta find the lightest section.
Well, here let's go back to, hold on a second. I'll go back to this, okay? Now, Gordon, repeat your question. Which like what I like to do when I go to the tables, okay? First thing I do when I come to this table, what's my first concern?
Is it gonna be the MR value?
No, the LU value.
The LU. Okay.
That's the most important thing. Okay, that is the most important factor, LU. Okay, after that, once I know my LU value, I can go look for my MR value. Okay. So for here, I know that we said that it was 4,500. So I come into this column here. These are all the MR values for this unbraced length. I try to find something that's greater than 363. Oh, here's one. Okay. Here's one right here. This is 375. I need 660. So therefore, my MR is greater than my MF. Then I keep going up. Okay. But keep in mind that this is going to weigh 74 kilograms per meter. Then I keep going up to see if I can find anything up here. If I can find anything up here that's less than 74. So everything up here seems to be greater than 74. So most likely that would be the lightest section. And then after that, I go check my VR and I go check my IX. You understand? For this one here. Is that okay, Gordon?
Yeah, but also there's like I didn't check with the VR and the VR, but what about the W530 that has a MR of 366 and it's 72
The a W530 by what?
by 72, just on top of your mouse. It has MR value of 366.
Yeah, the only thing is that yeah, you're right. Here, this would be a little bit lighter than this, right?
Yeah.
And the only reason I would stay away from it, see that little cross?
Yeah.
It tells you that this is a class 3 section, okay?
Oh, okay.
Like you can use it, Gordon.
Mhm.
If like it's good. If that's the choice you made, it's absolutely right. You follow what I'm saying? If a class 3 section is what you know, like and you're absolutely right. It is a very good choice. It's slightly lighter. Okay, I call me old fashioned, but unless I have to, okay, I would stay. I like to stay within the class 1 and class 2. I like when the whole section plastifies and not just the flange. Okay. And that's why I like to stay away from wherever you see these. Now, like I said, unfortunately, I don't have the new handbook. The way that they set up these tables in the new handbook that I read about is that now what they've done is they put in yellow what are the most available shapes. So that also helps you to make a better selection. You understand? So if you guys if ever you buy a new handbook, and you come to these beam selection tables, there will be, like, for example, I've never seen them, so I won't be able to tell you, but they will highlight which are the more available shapes, okay? And therefore, you should be making that also part of your decision making of what you're going to go with, not just weight, okay? So that's another nice feature about the new tables. And I mean, I should order a new handbook, but anyways, I should. Okay, so Gordon, you're absolutely right. So this is good, as a matter of fact here. And does the IX work and does the VR work? I guess it does, right? Because it's even deeper. So that should work. Because if this one worked, that worked. Yeah, okay. So good choice. Nothing wrong with it, Gordon. Okay?
Thank you, sir.
Oh, you're welcome. Thank you for pointing it out. There is even a lighter section if you want to go to a class 3. So thank you for pointing that out. Okay, so let's close this and let's go to the lecture. Now, here, I'm just going to continue because I want to show you, like how, I mean, we're going to continue with beam designs. Okay, we're going to continue with beam designs. And okay, so here, this is a typical layout. Okay, this is a typical layout of what you find. I mean, this is just 2 bays side by side, but big shopping centers, okay? Big shopping centers tend to have like spans of 40 feet by 40 feet, which is what, 12 meters by 12 meters, okay? And a lot of them like to have this, like, for example, this girder beam system and then have the steel deck going over it, okay? So this here, of course, is, just a partial plan view of that overall layout for a shopping center, supporting the floors or the roof, whatever. So here we have a dead load of 2 kPa and a live load of 2.4 kPa. And I think that's the live load that you require in a shopping center. The beams and girders are supporting finishes susceptible to cracking, so therefore your deflection cannot or should stay below L over 360. Now, design the beam 1 and camber for the dead load. Okay, the beam is largely supported by the steel deck at 300. This is a typo because usually spot well at every 300, but we'll leave it at 400. It won't make a difference. Okay, so here we go. So this is what really happened. You would calculate the dead load that this thing is carrying. You know that the live load for a shopping center, I believe, is 2.4 kPa, or for an office building, whatever. And therefore, now we're going to design the beam. So design loads, case 1. Okay, 1.4 times my dead load. Combination 2, 1.52, and times my live load. And then, of course, the higher of the 2 governs. So there's my design load. Now, WF is the factor load times the tributary area. And of course, if we come here and we ask ourselves, well, what does B1 carry? Well, it carries this much of the floor, it carries this much of the floor, and therefore the tributary width here is of course the spacing of 2,500 millimeters or 2.5 meters. Everybody sees that. Is everybody still having trouble seeing what the tributary width of a beam is? Is that okay with everybody?
Yeah, we're fine.
Good? Okay.
Yeah.
Okay, I'm happy about that. Okay, now, so here we go. So here we go. We have 2.5. That's where that comes from. I end up getting a WF of 15.3 kilonewton per meter. And of course, now I need to know my WL because I need to calculate the moment of inertia. Therefore, I take my live load. And like I said, guys, here you just use the specified load and only the live load. That's how you calculate deflection. Unless like for wood, it's totally different where they ask you to calculate the total deflection, but the deflection criteria is only half of this one. So here I have WL is 2.4 kilonewtons per meter times my tributary width, and I have 6 kilonewtons per meter. So this is for deflection purposes. Now, I've got all my loads. Of course, the next thing is to do a little bit of analysis, and WD, of course, I need this for deciding the camber. And of course, and there you go. And this thing is right in the way, so I end up getting 5 kilonewtons per meter. So now I've got, so this is to select my beam, and then this is to tell the guy how much to camber the beam by. So now, of course, WFL squared over 8. This gives me the a moment of 122.4 kilonewton meter. And of course, VF is WFL over 2. Okay. And now the deflection is L over 360, and this deflection equation for a simply supported beam that has a uniformly distributed load. And of course, here I would put WL as a value of W, and I'm calculating the IX value. And therefore, I end up with an IX of 72 times 10 to the 6. And like I said before, guys, when you're doing this, just make sure you're using millimeters here and always use a scientific notation of 10 to the 6, because that's how all the tables are in the steel handbook. So, and this is the only value you're going to see because this is at the top of the table. So now I've got my MF of 122.4. I got my, okay, and I got my IX. So the only thing I need to know now, what is my LU? Well, because it's being supported by the steel deck at every 400, my LU is 400, and LU is very, very small. So most likely I'll be able to use the first column at 122.4. So I go to beam selection table, clear the drawing. So, okay, so I come here and I start looking. So here, most likely these LU values, okay, there's nothing less than 2,500, so I'm not going to worry about it. So I keep going down until I find an MR value of 122. Oh, here, 126. Wow, this is pretty good, okay? And like I said, guys, the reason why they have these highlighted, because this is going to give you the best MR for all these, the other ones that are slightly heavier. Okay, so therefore this is the MR value, and of course your VR value and your IX value is here. So I think this is what I chose. Is this what you guys? Oh yeah. Well, okay. So this is what I got here. So W360 by 33. Why did I go to this one? W360 by 33. Oh yeah, 168. What was my MF value, guys? 122.4. IX was 72. Okay, and VX. Okay, so $133 by, okay, so here's 168. Oh, it's because, guys, do you see why I didn't choose this one here? Did everybody see why I didn't choose this one? Even though the MR is greater than the MF? Why is this one no good?
Your IX is less.
Exactly. In other words, you have to meet both conditions, and therefore the IX is not sufficient to give you a deflection of L over 360, and therefore this would not meet your serviceability requirements, okay? And therefore I would go up until I would get an IX greater of 72. So here my MR value is good, my IX is greater than 72, and my VR value, of course, if I take 80% of that, will be greater than my VF value. So that's why, okay? So there you go. So that's why I took a W360 by 33, because I have an LU, which is greater, of course, and therefore I can take the MR value of 168, greater than 144. 80% of 396 gives me 316, great. And this is what really, you know, led me to have to choose this one as opposed to the other one because of the IX value here, okay? And that's it, you've designed the beam. Easy enough. Now, what we're gonna do is for the camber, now that I've got my IX value, okay, I can calculate the amount of deflection this beam will have only under the dead load, and therefore I put in the values here. I end up getting 16.1 millimeters. And it's starting to be substantial, you understand? 16.358 of an inch. If you start adding that to the dead load of the, and there you go. So therefore, okay, so that means that you would ask it to be cambered by about 16 millimeters. You'll never get 0.1, so don't worry about it. And that's it. So now that you've designed this beam, and of course you can appreciate, okay, if a beam here, okay, has the same load, has the same geometry, okay, any other beam that has the same geometry, the same, okay, load, these would all be the same sizes. In other words, these would all be W360 by 33. Now, if this happens to be a perimeter beam where it only has half the load, well, if you want, you can redesign this one because it doesn't have the same load. And then this one would be the same as that one, would be the same as that one, would be the same as that one, okay? So if you want the perimeter beams, because they only have half the loads, you can redesign them and make them slightly smaller, okay? Now, you see here that this girder here, you see that this girder here is supporting all of this, okay? And therefore, and then this girder here is only supporting this, okay? And supporting this. So therefore, this girder here, and then if you want, you have to design this girder, and this girder here can be the same. That's why you call this one G2, because if you have a beam, you know, a schedule for your beams, you'd put B1 and you would specify what it is, B2 what it is, G1 what it is, and then wherever the G1 and the G2, that's the member that they would put in. Or you can put them right here on your drawing. It's up to you. Okay, some people like to have schedules and then just designate markings for the beams, you understand? That's up to you. So now, the dead load is the same, the live load is the same, the beams and girders, okay? Design G1. So now you need to design this, okay? Now, the only difference here is, of course, it's going to be the analysis. In other words, you're going to have to be able to analyze what the moment is, what the deflection is, and of course, because these beams, okay, because the load from the beam ends up creating a point load there, a point load there, a point load there, and a point load there. That's what happens here. So this girder G1 ends up getting a concentrated load and a concentrated load. And therefore, you have to analyze it with this configuration. That's the only difference, okay? Now, so here, as far as the dead load goes, well, same as before, okay? Same as before, okay? Now, what is a PF value? Okay, in other words, what is the value of PF? And if I go back here, okay, so the PF value, in other words, how much of a concentrated load do I get here of PF? How much of a concentrated load do I get here of PF? Well, it would be this area here, In other words, half of this would go there, 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 this would go there, that would go there, and therefore this becomes your tributary area that all the loads come to create this PF value here. And because these are exactly the same, then the PF here is the same as the PF there. Okay, so this is the tributary area that contributes to taking all this pressure, and because it is being, how can I say, the load path of this is from here to here, is being transferred here as a concentrated load from this beam. In other words, it becomes just a concentrated load, and that's what we're doing. So basically, so we have our factor load times R. So 2.5 was the width, 8 meters was the distance in other words, half, 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 half. And we end up with 122 kilonewtons. So that's the concentrated load that's going to be applied to the girder, right? Now, of course, what you can do now is, if you want, right, you can say, here's my beam, okay? Here's my beam, my girder. I have my load here. I know this is 122. I know this is 122. I know my span. I know this distance. Of course, I can go calculate my reactions. This is 122. I can go calculate my shear diagram. I can go calculate my moment diagram. And then I have to go calculate the deflection. So you can do it that way, you know, or of course, what I like to do is simplify my life. I like to use, I'm sorry, the live load. Oh yeah, sorry, we have to do this for the live load also. I'm sorry, I skipped a few steps. 48 kilonewtons is PL for the live load, and the dead load is 40. So now I've got all my three loads, okay? Well, in this case, I should say all my three forces that I need to do my analysis, and then determine these two to do my analysis, and this to determine my my camber, my dead load deflection. And of course, the best thing to do, what I like to do, is I like to turn to these guys here, okay? And of course, I look for a diagram of what I have, and therefore I can apply that diagram and all the formulas in that diagram to help me do my analysis. And therefore, this is exactly what I have down here, okay? This is exactly what I have down here. I have two loads, two equal loads. In other words, this now becomes PF. There are equally distanced from the reaction areas, okay? And then from this diagram, I can very easily know what is my V. So what is V and what is R? That's the value of P. So whatever PF value here is here, that is the PF value. This is the R value here, and that's also the V, the shear. Okay, so that tells you what this is. The maximum. Okay, so in other words, this is the maximum load here. You simply take your PF multiplied by the A value. That gives you MF. Wow. And then what I like about this is that when it comes to saying what is the maximum deflection, well, here's a formula for the maximum deflection. So therefore, that's the other thing I like about this, okay? So I can use this. In other words, this is P, this is A, the distance, okay? So that's where these beam formulas are very nice. They give you the equation so that if you have all the variables, you can go ahead and right away find out what your shear is, what your moment is, and what your deflections caused by whatever you have. You just have to make sure that the diagram corresponds to your problem, or I should say to your design. And therefore, once this diagram corresponds to what you're designing, then you're allowed to use all of this to do whatever you need in order to do your analysis. And that's what the beam formulas are for. So, so this is, like I said, what I like about this is that this is what I'm going to be using to calculate my IX. You understand? So that's the nice thing about these things is, so I get the MF is equal to PF times that distance A, and the distance A was 2.5 meters, and therefore I get my MF value right away. The VF is simply equal to PF, 122 kilonewtons. So I got my VF value. And delta is L over 360. And this was the equation that we had for the maximum deflection caused by two concentrated load equally spaced from the reaction areas. And therefore, here I would put the value of PL. A I know, the same A as I have here. L I know, A I know. E I know for steel. The only thing I need is my IX value. And therefore, I end up getting 360 PLA. Of course, I will leave the L in here this time because I can't cancel it anywhere. And I will leave it as 24E. And then, of course, now I tend to do this once. I calculate it, and then I tend to do it again to make sure I get exactly the same IX value, okay? Because, you know, very likely. And of course, I'm very particular on the units because I want to make sure that at the end, I end up with millimeters to the fourth. So I make absolutely sure that that cancels that cancels that. Excuse me. This goes up here, and therefore I end up with millimeters to the fourth. This and this together. So therefore, I know I'm on the right track. Okay. So that's the other thing I worry about. And then once I've done all of that, then I take the trouble of putting all this into my calculator. Until I do that, useless. If I know that my units don't work out, I don't care how many times you're going to do in your calculator. If your units don't work out, it's going to always be wrong. So keep that in mind. And now I work this out and I get an IX value of 172.5. So now I don't know how you would have calculated your IX value if it wasn't for the beam formulas. You know, there are other ways you can do it. I don't want to get into it, but it's even very, very complicated, but it can be done. Okay. Here's my IX value. Here's my MF value. Okay. Now, what is the LU value in this case?
Sir,
Yes.
isn't it for meters?
You say it's 4 meters, the LU
Well,
value?
well, I mean, I didn't read the problem, but isn't it specified at midspan?
Well, like here, if I go back to problem number 2, right? I'm going to go back here. What is the LU for girder number 2?
It's 2.5 meters. Okay.
Okay, so
Yeah.
everybody sees that? Okay. Now, right now, if like for example, right now, if there's nothing else attached to this, okay, it would be 2.5 meters. Everybody sees that? Okay, in other words, this beam will allow you to support the girder 1. This beam will allow you to support the girder 1, and especially that. So in other words, the maximum LU that G1 has is 2.5 meters, okay? Now, if I happen to be putting some, you know, if I happen to be putting some steel deck on top of these things, okay? Okay, and I also attach the girder to the steel deck, then I can change my LU. But if I don't attach my girder to the steel deck, the LU stays at 2.5 meters. Okay, so that's what it is. So it's the minimum LU value you have right now is 2.5 meters. And therefore, now I can go to my table. So let me just make sure something. I want to, so MF we said was 305, LU is 2,500. Okay, IX is 172, and the VF, very rarely that it governs, so I will just worry about that after. So I come here, oh, why did I? Oh, this is not a hyperlink. Sorry, guys. I should have gone to the I thought it, I'm sorry. I'm gonna go and get this one. Oh, sorry. Okay, so the beam selection table. So we had an LU of 2,500. So we're somewhere in this area here, right? And we have an MF of 305. So I got to go up. 2,500, 305. So here, this is that means that when I'm seeing the blanks, okay, so this is no good. So that means that all of these are probably good. So I can go for a W460. So that's how, so I go to my LU value here of 2,500. I have 365. I need 305, so that's good. And then after that, I have an IX value of 255, which is greater than the IX value that I need, and most likely, so this is what I would choose right here. Like I said, guys, when I come to the tables, I look under my unbraced length first to find an MR value, okay? And then after that, of course, take the bold, okay? And then after that, check the IX value, see if it's sufficient, and then of course the VR value, okay? So that's how I got that. Okay, so here we go. Okay. I thought that was a hyperlink, and it was a hyperlink, but for some reason it changed on me. Okay, so therefore I have 365 versus 305 is perfect. This is perfect, and this is perfect. So everything works out. So therefore my girder can be a W460 by 60. Now that I know that this is what I'm going to be using for my girder, of course I can now go calculate deflection. Okay, for here now it's working. Okay, so I'm not I'm not going to bother going here, but it's the same equation that we had before with the WL here. I'm not going to bother going there. It's exactly the same equation. Okay, and therefore the only difference is that instead of putting PL in here, I will put PD. In other words, a dead load caused, imposed on the beam, and therefore I would put 40,000. Now here again, guys, be very careful. Okay. Be very careful about, okay, the units, newtons, therefore the 40 kilonewtons became 40,000 newtons, okay? And if you don't do that, of course, your units are not going to work out, okay? So that's the other thing about, nice thing about units. People put 40 here and then all of a sudden they end up getting 0.0117, that's what happens. And of course, that would be wrong. And Anton, you have a question?
Yeah, question. Why is L in this formula 7,500?
Okay, so let's go back. Let's go back. We'll have to go look at the geometry.
Okay.
Okay. I might have made a mistake, so I'm glad you picked up on that. Okay. Oh. Okay, because the span of G1 is 7,500.
Oh, okay, because I thought, okay, sorry, my bad.
Okay.
I thought, because I was still looking at like that B2, B1, they have 8,000. Okay, that's why I got it.
Okay, no, but I'm glad you asked, Anton. don't get me wrong. Like I could have made a mistake, put the wrong span in. So I'm glad you asked. But that's where it comes
All right. Okay, I see. Thank you.
Fair enough. So
So
yes, Jan, go ahead.
I also have a question. Like, since the span is 7,500, how come when we're calculating the tributary area, we're taking 2.5 meters times 8 meters?
Okay, so let's go back to that. I'm glad you asked. Okay, because look, what you have to do. Okay, this is the span of the girder. We agree? That clear in your head?
Yeah.
Okay, because I have a column here. I have a column here. Okay. And this girder is being supported between the two columns like this, okay? And that means that from there to there, I got 7.5 meters, okay? Right now, I got these two beams that are coming in here like this, and those two beams that are coming in like that. You see? You follow what I'm saying? So the reaction of this beam and the reaction of this beam will give me the reaction onto the girder. In here, okay? So I could, like for example, go back to problem number 1, if you have written the values, take your VF value and then multiply it by 2, and that's going to give you the same PF value that we had here. And if you don't believe me, I'll do it right now, okay? Like if I go back here, go back here, 61.2. That was my VF value from B1, okay? And if I come back here, and okay, if I take 61.2 times 2, what do I get?
122. That makes sense.
Okay, so exactly. So in other words, I either calculate the reaction from B1 or I can take the tributary area. Okay, I can take the tributary area that is causing a concentrated load on the girder. And therefore this here is half of this. So this is 1.5 meters. I'm sorry, 1.25 meters. And this is 1.25 meters, which gives me a total width here of 2.5 meters. This here is 4 meters. And this here is 4 meters. And therefore this area here is 8 meters squared, 8 meters by 2.5 meters. That's the area that is being all brought to that one point because of the two beams.
Okay, thank you.
Now, is it clear? Jan,
Yeah.
I want you to see this, you understand? That to me is more important, you understand? I want you to be able to see. And like I said, if this is B1, right? And I did all the analysis for B1, well, R here is equal to V, right? So therefore, if I take the V from B1 here and I take the V from B1, the shear from here, I'll get the same value there. So I don't care how you do it, it's going to give you the same value. But sometimes you might not want to go back and you want to say, well, I want to be able to calculate it right away. I simply try to find whenever I want to convert a pressure into a concentrated load, I know I have to multiply that by an area. And of course, the tributary area that is causing that concentrated load is half, just like we do, like half, half, and then half, half. And then that's how you get the tributary area.
Yeah, thank you.
No, you're welcome. I mean, don't worry. We're all here to learn.
I have a very stupid question.
No, there's no stupid questions. Go ahead.
This one it is. Okay, for the B2, like the beams at the edges of the girder.
Yes.
Okay. Like won't some of the weight be transferred to the column beneath? Like because the girder is placed over two columns, right?
Okay.
So like the weight is not like distributed equally between like
Okay, Nermin, you're asking the question. Okay, now look, B2 is being transferred right into the column, will have no effect whatsoever on G1. Okay, so everything that B2 carries will be carried by the column, so it will affect the column. Now, if you really want to become not anal, but if you want to become really academic about this, I shouldn't use the word anal, but if you want to become really academic about it, okay. And I don't do this, but if you look at it, and this is more like we do this in reinforced concrete. If you really want to minimize the load, okay, like in reality, okay, like this is the load carried by B2. And then this is the load, okay, carried by G1. So you do have this little bit of constant, like you do have this little bit of load that I'm assuming goes all into B2, okay? But here, as a matter of fact, you do this when you have reinforced concrete. But for steel, since my deck is going this way, okay, the load is actually getting transferred to this beam, and therefore I don't worry about this having any effect on G1. But for reinforced concrete, if you really want, you can start really like getting these trapezoidal shapes. And at the end of the day, Nermin, it just complicates your life. It does not even do, you don't have much benefit for going through all that detail. You understand? But for steel, the steel deck is going this way, and therefore the load is being transferred there. There's even, so that's why I don't even bother with steel. Well, first of all, for steel, it doesn't work. But if I really look at tributary area in concrete, I can break it down into these trapezoids, you understand? But don't worry about it. If you don't do it, if you do like you simplify your life, you say half, half, half. At the end of the day, you won't have a problem. Trust me. If you do everything correctly. I don't know if you understood me, Nermin.
Kind of.
Well, okay. Tell me, like in other words, you're asking me what does B2 you asked me, what does this beam do to this one? Is that what you're asking me?
Yes, because when we were like, you were saying that the weightage should be distributed equally along the G2 and G1, right?
Well, my steel deck is going like this, right?
Yeah.
Okay, so all the load that's being put on the steel deck, what's happening to it is being transferred to the beams. This is what they
Beams,
call
yes.
the load path. You understand? So if somebody steps, like for example, if somebody's stepping here on the deck, right? What's going to happen? That force is going to go partially here and partially there, right? Then once it gets to this beam, what happens with that force? That force goes to here, and then it goes all the way to here. You follow?
Okay.
So basically, what we're saying here is that what's the load path? The load path is that all the pressure I have on this floor gets carried by these guys, basically, right? And then these guys transfer it to these guys, and then these guys transfer it to these guys, and so on. You understand?
Okay. Okay. I can picture it now. Yeah.
You
Okay. I got it.
understand? Is it clearer? I don't expect you to get it the first time, but it's a little
I got
clearer. Okay.
Yeah. Yeah. It is. Yes.
Okay, so you understand why this guy has no influence. As a matter of fact, when we're going to be doing the lab, okay, I'm going to show you that if you remove all the forces that you applied at the reaction areas in your ADA and you run the analysis for your girders, you're going to get the same results. It won't make a difference because that's going straight into the reaction area. In other words, that's going straight into the column. The only difference is that if you don't add them there, then when you want to use those values to design your column, you won't have the total load for your column. But I can tell you that, like any load that gets applied right here, okay, it's only going to affect the column. It's not going to affect B2. It's not going to affect G1 or anything, okay? And, if you want to convince yourself, like, take your ADA, remove all the concentrated loads right over the reaction area, run the analysis and see if you get exactly the same MF values and you get the same VF values. And I can guarantee you will, okay? But the only thing that you won't get the same is the RY values. That's going to be different. Okay, so far so good, guys?
Sir,
Yes,
quick
Andrea.
question. Your new MF, VF, and live load formulas, did you get them off the beam diagrams and formula
Well,
PDF?
that's exactly where I got them. It sounded like what I did is I said to myself, okay, like what I did was I said to myself, okay, what I did is I looked at this and I said to myself, okay, this is what I have. I have a beam that's simply supported like this, right? Okay, and I got a concentrated load here, P. I got a concentrated load here, P, that's equidistant from my reaction area, A, right? So therefore, since I have this diagram, is there something in the beam formulas that I can use that I can go get all my values, right?
Okay.
So since that's what I'm actually trying to analyze, like for example, a beam, here's R1, here's R2, okay? And I have a load here and I have a load here. And this distance is 2.5 meters. This distance is 2.5 meters. This distance is 2.5 meters. The span is 7.5 meters. Now, of course, I could do, like here, okay, and this is my PF value of whatever it is. I forgot 122, okay? So this is equal to 122. If this is equal to 122, and then that's and then here's my shear diagram. Understand? Okay, there's my shear diagram. I can do it, and then after that, here's my moment diagram, and then like this is and so on. So I can do that, and then I say, what do I do for deflection? I mean, I can do that kind of, I can use the free body diagram to do my analysis, but then what do I do about deflection? So then, like instead of breaking my head, what I like to do is I like to go to these guys. I like using this. I use this constantly. Understand? Like here, a simple beam, two equal concentrated loads symmetrically placed. In other words, they have to be, in other words, if your diagram is exactly what you have, what they're saying here, use these formulas, you'll get the results of what you're looking for. So here, if you look at R is equal to V is equal to P, and of course us is PF, okay? So in other words, the shear here is equal to the reaction is equal to the value of P, and that makes sense. The maximum moment here is simply your force times the distance A, which is exactly what it is, because if I take that times that, it gives me the moment, so that's P times A. And then the maximum deflection of the center, here's the equation for deflection. So I use this to calculate all my deflections because I wanted to calculate the maximum deflection. So I get all of that from the beam formulas. Okay. Adriano, is that clear?
Yeah, it's clear, sir.
Like these tables, like if I happen to have one concentrated load here and it's not in the middle, I can come and use this to do my calculations. You understand? And if I have one that's right in the middle, I'll use these equations. You understand? So sometimes I do have a situation where I have a simply supported beam and I have here a concentrated load because I only have one beam down the middle. So I'll come here and I'll use this. You understand? And I'll calculate the maximum deflection based on this formula. So these things are pretty useful. So instead of spending $3,000 or $4,000 on an ADA software, in most cases these things can solve your problems. You follow what I'm saying?
Yeah, for sure.
It's pretty amazing, so. Yeah, it's like ADA is great when you start getting to statically indeterminate beams and you start getting into a lot of load cases and a lot of repetition, this and that. Yeah, spend the money if you know, like if you're going to save yourself some time and therefore you'll be a little bit more productive and you'll be able to get more contracts to justify paying $3,000 for your ADA. Okay. So that's what these things are very. I introduced this I introduced this in structural analysis in year 2 because I wanted. That's where you get to see them, you get to learn how to use them, and I show you that in real life these things are very, very practical. You know, they're a great source of information. So now we oh yeah, like I said, I apologize. That wasn't a okay. So now, and there we go. Now, since I have my IX, like I said, since I have my IX, now I can calculate my camber. I won't bother going back to this one. It's the same formula, but the only difference here, I put PD instead of PL, and I calculate because I have the value of IX, and therefore I end up with 11.7 millimeters. Okay, so guys, I bring this example to show you, like in situations where you have beams that are being supported by girders, the beam itself simply supported the same way we've been doing it. The girder, well, it becomes two concentrated loads. Go through beam formulas, use the beam formulas to calculate your deflections, and you solved your design problem. Now, I think this is one last example I have here. Okay. Determine the lightest white flange beam that is simply supported that spans 8.2 meters, which carries a dead load of 1.8 kPa, including the self-weight of the beam and a live load of 3.6 kPa. The tributary width of the beam is 8 meters, which is pretty significant, and a live load deflection of L over 360. The beam is statically, the beam is lightly supported at every 2,500 millimeters by the joist. Great. So this is, a typical roof where you have the joist space at 2.5 meters, and you have, what's the dead load? Pretty high. Okay, 3.6. Okay, so this could be a floor, mechanical floor, and therefore, anyways, pretty high. So, okay, so here, the load combination 1, again, okay, I do this because, like I said, eventually when you guys start realizing that the dead load doesn't exceed 10 times the live load, then it's always going to be combination 2 that's going to govern, okay? But I like to do this to remind you that there are, you should always check the 2 and make sure. Now, of course, the WF is the factor load times the tributary width. And this is, of course, 7.2 times the tributary width we said was 8 meters. So therefore, we have 61.4 kilonewtons per meter. That starts being substantial load. And our live load, of course, is only the specified live load of 3.6 kilonewtons per meter times 8 meters. It's 22.8 kilonewtons. 20.8 kilonewtons per meter. Now I've got my WF, I got my WL, and of course, because it's simply supported, I have WF is equal to L squared over 8. And of course, excuse me. And this gives me 514.4 kilonewton meter. So it's starting to be a significant moment here. And VF is WFL over 2, 250.9. And of course, delta L is L over 360. That's the deflection for materials susceptible to cracking. And this is the deflection formula, the maximum deflection at the center of a simply supported beam that has uniformly distributed load. And therefore, I isolate the IX, and I get 360 times 5 times WL, L cubed over 384. And again, this should work out to be millimeters to the fourth. And if you look, it does give me millimeters to the fourth, and therefore I'm on the right track. And like I said, this is the only thing you should worry about, because kilonewtons per millimeter is the same as a Newton per millimeter. So if you forget to do this, this doesn't hurt you. But if you forget to do this, this will hurt you. Because your MPa here, your 200,000 is in MPa unless you convert it to, like I said, kilonewtons per millimeter squared. You understand? And then you don't have to worry about it. So now I have an LU of this, so let me write this down. So I have an MF of 514.4 VF, well, that's like I said, in IX of 372. Okay, so now, and I go with my 2.5 meter LU here, and that's where, of course, so LU of 2.5, like I said, I look under here, okay? So this seems to be good here, okay? So nothing's good down here. Oops, sorry. So for a 2.5 meter, the first thing I hit here is a W530 by 74. And of course, because see here, the LU is 2040. And now let me go check above. So I do get higher values here, but everything here seems to be heavier, 8296 as opposed to 74. 82, like for 2.5 meters. Yeah, these are all higher. They are all MR values greater than what I need, but so are all the okay. So in other words, it seems that the lightest section I can choose is a W530 by 74. Is that clear to everybody?
Yeah.
Yeah,
Yes,
good.
sir.
Okay, yes. Clear? Guys,
Yes,
like I said.
yes.
Okay, so in other words, guys, it's always your LU, most critical, piece of information when you come to these tables. Then your MR, okay? Because if your LU is correct, your MR is correct, and if you accidentally happen to take a beam where your IX is not going to be what your IX required, well, at least it won't collapse on you. It's just going to maybe deflect more than it's supposed to. That's all. But if your LU is incorrect, your MR is going to be incorrect, and then it can be a serious problem with the strength of your beam, and therefore that can become catastrophic, because then it's going to be a question of strength, no longer just serviceability. Serviceability, if it becomes an annoyance, there's ways of fixing it. I can show you how to do that. Okay, I fixed quite a few beams that had a serviceability problem. Okay, and it's not that hard to fix. And you simply have to, if you guys are really interested, I can show you right now. Like, so that, okay, so for example, if this is my beam here, okay. This is my beam here, and all of a sudden my beam doesn't have the stiffness required, okay? So what you do is you take plates, you calculate the plates required, and you take plates and you weld them at the top and at the bottom here, like this, because of course you got members sitting here, and you try to increase the moment of inertia. That's you take your IX required, and you do like the same thing. You calculate what the size of plates you need in order to get that IX required. You weld them all around. You increase the moment of inertia. Some people like to use round bars in here. They just put round bars in here and then they weld them. So it's very easy to upgrade. Well, easy. It's not that complicated to upgrade the IX for a beam by adding additional steel to it. And like I said, it's very easy to do. If you just have to calculate the area required and all that. And of course, I'll show you when we get into joints how you calculate the welds here and all that. And so if you screw up on the IX, not a problem. It's gonna bounce around, it's gonna deflect, people are gonna start complaining, but at least it won't collapse. Screw up on the MR, and all of a sudden it starts to, sag excessively. Of course, it's going to sag excessively because your IX is not even the right one. And all of a sudden it might even collapse under the snow load because people won't be there to see that it's, deflecting excessively, and that becomes a really serious problem. So keep that in mind. Okay. Always worry about your LU, and then worry about your MR, and then worry about your IX, and then of course always check your VR.
Sir?
And still, yes,
Sorry
Omar.
to interrupt, but
Yeah.
quick question here. Let's say if like it sagged a little bit, like let's say 4 inches, okay?
Get the hell out, Omar.
Let's say
Omar, I'm telling you, get the hell out. If you're telling me it sagged 100 million, 4 inches, okay, and in a span of how far? Like
at least 12 feet.
get the hell out.
Okay.
You
So
understand?
there's no solution to fix that. Just leave, basically.
No. What I'm saying is get the hell out. You understand? And then after that, like what I'm saying is that, wow, you're asking me. Look, what you're telling me is that if I do it here, like, sorry, but like what you're telling me is that you have how much of a span did you say you had? 12 feet?
Yeah.
Okay, so 12 feet. You're talking about approximately what is it? Hold on a second. 12 times 0.3048. So you're talking about 3.66 meters here, okay? Or let's say 3.6 meters. L over 360, let's say you wanted to check for deflection. That means you got 3,600 divided by 360. Therefore, this thing should be sagging about 10 millimeters. And you're telling me that you got 100 millimeter sag. You understand? What is that telling you, Omar?
Wow, that's excessive, basically.
Yeah, exactly. Get the hell out. You understand? Don't wait until it falls and that you might be under it or on top of it. Okay. Then of course, if it hasn't fallen and it's just excessively sagged, okay.
Yeah.
I mean, it's going to take one hell of an engineer that's got big kudos to go in there, okay, and tell the workers what to do. You understand? So normally, if that would happen, if it hasn't fallen down yet, and all of a sudden there's a there's a way of trying to lighten the load or whatever, okay, and then after that, what you do is you go in there and you take shoring material, you know what I mean by shoring material. You can take these jack posts, right?
Yeah.
And you go start putting them underneath your beam. You understand? You put one right in the middle to start off with, and you start, raising it up and make sure that that jack post can actually carry. I would calculate, for example, based on the deflection, what is the load that is being applied to this beam, and therefore I would make sure that this jack post has the capacity to push it up straight. Understand? And then if I can't rely on one jack post, then I would put maybe 3 of them. Understand? And then go up like a little bit here, a little bit there, a little bit there, until it goes back up straight. Have the whole beam shored, and then after that, decide whether it's worthwhile reinforcing or if the whole thing would have to be replaced. You understand?
Okay.
So, I mean, Omar, 100 millimeters, like you would panic even if you know what you're doing. You understand? The reason why I wouldn't panic, I would just see it and I'd leave.
Okay.
I wouldn't waste my time panicking. I would just get up and leave. You understand? That's what I would do. So, how does that sound? Okay. And that's the nice thing about steel, guys, is that it is a nice ductile material, and if it happens to be under-designed, okay, one of the things that's nice about steel, because it's a nice ductile material, is that it will start yielding, okay, it will start going past its yield point, you understand? And that's where you start getting excessive deflections. Like I know you guys have a hard time relating this, but what this means is that, okay, I know I'll explain this at the end of the class so you guys can get a better understanding. Let's finish the problem because we're diverging here. Okay, I just want to make sure we finish the lecture just in case. Okay, so here we go. So we said a W530 by 74. That seems to be the lightest one. And that's because the LU was, for an LU of 2000, which is what the LU that we've provided, right? We can take the MR value of 523, which is greater than the MF value. Great. The VR value, of course, is really good. No problem there. And of course, the IX value is more than what we need. So this beam would be adequate. And that's it. So guys, assignment number 2, I think will be shipped out sometime at around 9:45 today. Okay. And I appreciate that most of you at least downloaded the assignment, except for one person. And I'm telling you that next week, I will not be providing the PowerPoint file anymore. I will only be giving you the videos. So keep that in mind. I will give you all the tables that go with the PowerPoint, but you won't get the PowerPoint per se as of next week and for the rest of the weeks. Okay. I got my reasons for that. I won't explain why. So keep in mind that that's what's going to happen as of next week, both for wood and for steel. So, and this will be the last time you get the PowerPoint for this lecture here. So does anybody have any questions on the lecture before I go back and explain the thing about ductility? Is everybody good?
Yes.
Okay. Okay, so here we go. I'm going to stop sharing. I'm going to put the video on pause because I don't know if you guys want this to be part of your video. If you care to, I might as well keep it as part of the video. Okay, stop sharing. Okay, so okay, now just so that you guys, okay, I know you've seen this in physics. And you've seen this in physics. I'm sure you did. Where you saw this line here, and then this, and you saw this. Does everybody remember this in physics?
For the yield.
Exactly. In other words,
Yes, sir.
very good. Okay. So what this means is very simple. Okay. So this here is the stress level of the steel. Okay. Now, when we say that we have steel that's 350 MPa, what does that mean? Anybody have any idea? Like right now?
That it can go to?
Oh, it can go even more, but what does it mean 350 MPa, Rena? In other words, we're using, when we say Fy or is equal to 350 MPa, what are we saying?
So, like what I understood is like that it goes to there and then it starts like to, I don't remember the exact term, but like it would like break afterwards, right?
Well, okay, Rena, you're on the right track. What you're saying is you're on the right track. You're answering half the question, so you're doing very well. Okay, you're doing very well. Okay, what this means is that if the stress in the steel, okay, if in the stress in the steel stays below 350, I'm going to change color here. Okay, this is what they call the elastic range of the steel. In other words, as long as the stresses in the steel stay below 350, it acts like an elastic. You load it, it stretches. You load it, it stretches. You load it, it stretches. And then all of a sudden, if you take off the load, what's going to happen to the steel? In other words,
It'll go back.
exactly. Like, so for example, if in theory I do not load the steel, what would be the deformation of the steel? Zero.
Zero.
Exactly. You follow? In other words, if I don't apply a load, it's zero. So in other words, remember what strain is? Okay.
Yes, the deformation basically.
Okay. Okay. But okay. Now in steel, okay. Okay. Did you guys learn this in physics?
Yeah.
Yes.
Okay, so now you know that for structural steel, right? You know for structural steel that E is 200,000 MPa. That's an assumed value, okay? Fair enough. Now, if I know like how much stress I'm putting on my steel, okay, I know how much it's going to strain. In other words, how much it's going to stretch. That's all they're saying. And if I want to know that value, well, this is how I calculate it, okay? So I take that divided by E, and it tells me how much is going to deform the strain, okay? Now, all of a sudden, so as long as, if I have a beam here, okay, and where's my colors? And I put a load, okay? Okay. When I put a load, this load causes stresses in the beam, okay? And as long as the load I'm applying here, okay, the stress is here, and to calculate the stresses is very simple, okay? Stress is equal to M over S, okay? So therefore, if I know the moment and I know the section modulus of my beam, I can calculate the stress. As long as I know that this stress stays below 350 MPa, I remove that load, it should come back to its original position. So up to 350 MPa, this thing will act like an elastic. Go stretch out, take off the load, come back. Leave the load there, it's going to stay stretched like that, and so on, okay? Now, what this means is that when I hit the yield point, if I keep adding some load here, well, the relationship is no longer linear. In other words, for a very little amount of load that I add, the deformation gets bigger. So therefore, it's no longer linear. In other words, it's not like I put so much weight, I get so much deformation. I put so much weight, I get so much deformation. At that point, I put a little bit of weight. Ooh, look at the deformation. Okay, and that's what this is. In other words, here, the steel starts to yield. Okay, and then all of a sudden, because of strain hardening in the material, well, all of a sudden it starts going, but see, so in the elastic range, the deformation is very little. Okay, so if you start seeing that all of a sudden it has deformed by like Omar by 100 millimeters, guess what's happening to your steel? You're somewhere in here. You follow? In other words, if that thing started to sag excessively, that means that your steel is now probably in the plastic. So here it's elastic, and here it's plastic. In other words, it behaves like putty, you understand? It just keeps stretching and stretching. And then all of a sudden, because of strain hardening in the steel, it requires a little bit more load for the amount of deformation, and then it reaches a maximum. And then if you keep going, and this here is the tensile strength of the steel, okay? And we'll learn that, okay? You'll see that you have Fy, which is 350, okay? And then when we get into tension members, we'll learn about Fu. I'm not swearing at anybody, that's what it's actually called, okay? This is, okay, and this is, okay, and then we have, this is 450 MPa. Okay, so and that's the tensile strength of the steel. Okay, so this is the yield strength, and that's the tensile strength. And that's why when it gets into the plastic range, the steel hasn't yet broken, because it has to actually, oh, sorry, like, okay, it actually hasn't broken. This is the FU, the ultimate tensile strength. Okay, and then after that, if you keep loading it, it's going to break. And that's what happened. That's the breaking point. So that's what this diagram is supposed to make you appreciate, is that as long as I stay within that 350 MPa, as long as I stay within that 350 MPa stress range, the thing's going to behave like an elastic. It's going to stretch, take off the load, it's going to come back. Stretch, come back, stretch, come back, stretch, stay stretched. If I go over 350, it's going to stretch. And then all of a sudden, if I happen to stop here and I take off the load, well, some of that deformation is going to be permanently, and that's how they camber the beam. What they do is they camber the beam, and they stretch it into this part here, and that's how they get the camber, and that becomes a permanent deformation in the beam. And then when you put the load, it comes back to its, you understand? And that's what they do to camber. They actually bring the stresses up to this range here, and they can actually say, well, if you want 8 millimeters, they know how much they go into it. They want 10 millimeters, 12 millimeters, and so on. So when they camber the beam, they actually stress it into this range here, and then when they remove the load, there's some permanent deformation in the beam. It has not affected the strength of the beam. It only has affected its deformation. Therefore, I have deformed it like this. And therefore, when I put the load back on, it's going to come back straight. I mean, guys, to me, when I first came across this, I said, "Fuck, ingenious, ingenious." You understand? Look at this. Let's play with this range to get camber. Let's stay within this range to make sure that our beam stays elastic, and let's have this built into our design so that if I start seeing excessive deformation, it's telling me get the hell out. And that's the nice thing about ductile materials, is that it also has a deformation that warns you of a situations of overloading. And that's what's really nice about, you know,
But sir,
yes.
quick question. So if they support this element when it deflected, they support it with another, like the same kind of beam. Is that gonna help or no?
What do you
Let's
mean?
say,
What do you mean? I'm
like,
sorry, Omar.
you
Like,
know, they duplicate, like they saw the deflection, so they added another element on top of it. Do you think that would help underneath, like to support it?
you're talking about like if the beam that you were telling me about before that has 100 millimeter
Yeah,
deflection.
yeah, yeah.
Oh, like Omar, like now you're getting into a situation that somebody royally screwed up on the design of a beam. You understand? And you're asking me what would be the best corrective work, right?
Exactly.
Okay, well, the best corrective work is it all depends on the constraints of the project, Omar. So there's not one answer. You understand?
Okay, I
But
see.
if you're asking me like what can you do? Okay, what can you do in this situation? Okay, is it maybe adding more beams to support the floor load and reducing it on that one little beam? Is it replacing that beam completely? Is it like upgrading the beam by adding more plates and stuff to it? Omar, there's like what you're asking me is very, very particular to the job. You understand? And then what it always boils down to is that what would be the most economical way of repairing it? So that's another factor. So
Okay.
Omar, there's no
Okay.
there's no one answer. You understand? There's no one answer. Like I should have asked you, how would you repair it? Just to see what you would give me as an answer.
May I would like at the sides I put like angles so to help supporting the sides first, and then like
Okay,
from
hold
the
on.
top.
Let me share the screen with you, and then you can show me what you're trying to. Okay, hold on a second. Let me. Hold on.
You can just erase the board. I can annotate on it.
Well, I have to allow you to annotate. I forgot to do that. Okay.
No, I can annotate. Look.
Oh yeah. Okay. Great. Great. I guess I did ask. Okay. So go ahead. What would you do?
Okay, so I'll show you what I can do. So I put, so let's say this is the beam,
Okay.
and then I have a column here
Okay.
and a column here.
Okay. Great.
So the first thing I would do is support it like this, 1 and 2,
Okay.
and then and then and then maybe add another like sorry, let's do this, another element underneath, another like not column, another beam underneath it.
That's possible.
That's the only thing I can think of.
That's possible. Okay. Now, when you put this beam underneath, aren't these things going to be in your way?
No, yeah, that's true. That's true. I'm just saying, like,
I'm just like you understand what I'm saying, Omar. Like you're okay. The other thing is that this knee brace that you're putting here. Okay, this knee brace that you're putting here. This is called a knee brace. Okay,
yeah,
how's that going to affect your column? Is that going to maybe create a lateral load on your column that your column's going to fail after?
yeah. Okay.
Okay, so I'm just see, Omar. Everything is particular to the site. If you tell me that I have, so if you're telling me that I've got a big beam here that sags like this, okay, like that, right?
Yeah.
Well, the first thing you worry about is you go in there and you try to shore it. Just shore it. Make sure it doesn't fall.
Okay.
That's the first thing. You go in there with jacks. There are these jacks that can hold up to like 10 tons each. You understand? If you need to push like 30 tons, then you go in with 3 of them. You understand?
Yeah.
Okay. So first thing you do is you make sure that the thing is shored properly. You understand? And that's assuming that the floor can actually take that load. Because then you have to
Okay.
check to make sure that underneath you're not creating another problem. That's why, Omar, like it's very specific to the job site. You understand? I can't give you a solution. You understand?
Oh, okay, okay.
See, like if you tell me that you have a slab on grade here, okay, and all of a sudden the slab on grade can carry a certain load, then I have to make sure that the pad I put here is, doesn't affect the slab on grade. And, so these are all little things that you need to calculate. You understand? You just don't go in, like, all I'm saying is that the first answer to this problem, when you start seeing it deflecting 100 millimeters, guess what, Omar? Get out. That's the first part. That's the first solution. Get out. The beam is telling you, I'm about to fall.
Okay, I
You
see.
follow? And then afterwards, like once you get out and you think that it's like most likely if the guys go in there, okay, most likely they're going to go in there with something that probably have a cage over them so that they're safe, that if something happened, at least it falls on the cage, it's not going to fall on them. I wouldn't send a worker in there without some kind of measure that he's protected.
Yeah.
You follow what I'm saying?
Yeah.
So like, for example, there's probably these vehicles that have these big cages, and I have to make sure the cage can actually support, because then I'd be able to get an idea of how much of a load would come down on their heads, and make sure that the cage that the truck has that can actually support that, so that if it does come down, it falls on the truck and won't kill my worker. So that's my first concern, safety, you understand? And then once I worked out the logistics of safety, and then and then making sure, like you said, like you put this here, and then you ask yourself, okay, then once I put these knee braces here and all that, and then you worry about, you understand, like, because once you start shoring and everything's shored properly, then you start breathing. Then you have time to go in there and find a solution. So the first thing you have to worry about is that you're going to let it collapse, and if you're going to let it collapse, so be it. As long as there's nobody in the building, I don't care. See, Omar, as long as nobody gets hurt, the rest is just a question of money. But if somebody gets hurt, then it can become criminal negligence. It's no longer just money. Is that clear in your head?
Yeah, it's clear. Yeah,
okay.
yeah.
So, guys, I know that I hope you appreciated what I just